Hi everyone, today we are going to do our DSC lab, differential scanning calorimetry, and I'm walking again. So this lab is meant to kind of do two things. Elucidate kind of concepts about generating phase diagrams, which can be very obtuse, but also talk about the thermal properties of a very interesting type of material, phase change materials, which are very ubiquitous and used widely. So we're going to be putting materials in this, measuring thermal properties like melting temperature, heat of fusion, liquidus temperatures, solidus temperatures, and then you're going to do a excellent poster presentation for this lab. So we are going to be working with two polymeric materials, which is something that's very uncommon. When you think of phase diagrams, you think of metals, but we are going to be working with lauric and stearic acid, and you can look at the chemical formulas in the lab handout. Now, this lab, and many of the labs, if you read our labs, and I know all of you do, you read all the lab handouts thoroughly, right up until the very end, you'll notice that in the acknowledgement sections, one person kind of shows up repeatedly. That's Dr. Geetha Barrera, Professor Geetha Barrera. She was my instructor first as an undergraduate student. She paid me a very nice compliment on one of my actually my poster, the same poster that you're going to do. And really, if it wasn't for her, I would never have gone to grad school, and the rest is kind of history there. So I'm no Geetha Barrera, but I do try to imitate her. So this lab, she really developed herself. She has the best experimental hands that I've ever seen, and I was fortunate enough as a graduate student to basically assist her with this lab. So again, I'm no Geetha Barrera. My hands are never going to be as good as hers, but I just want to kind of pay my utmost respect to someone I really consider a very, more than a mentor, someone critical, I think, in my academic life. So with that, we are going to mix, to create a phase diagram, we need to vary concentrations. So we're going to look at different concentrations of lauric and stearic acid, respectively. And we're going to be looking at weight percents. So we are going to take different weight percents. So if it's 10 weight percent lauric acid, if there's 100 milligrams, that means 10 milligrams are lauric, 90 milligrams are stearic. So we're going to take some samples from here, we're going to measure them here, and then I've actually, as such a kind professor, I know everyone thinks that, especially when it comes to exams, I'm super kind. I've already made these samples, 30% lauric or stearic, 70% lauric, 60% stearic, 40, etc., etc. And right now I put it on a hot plate above 100 degrees C, and I'm melting these samples. So you can kind of see this right now, but they're going to turn into a clear liquid. And actually, you can kind of start to see, look at, some of these are melting before others. It doesn't matter depending on the amount matters too, but interesting, huh? Some are melting before others. So it looks like there's some difference in thermal properties. Look at this guy, look at the 50-50. It's already gone. Here, I'm gonna move this aside. Let's look at 50-50. Look at that, already clear, just a couple minutes in. So, we are going to melt this 3 times, and we're going to mix well so that we have a homogeneous solution, and then we're going to prepare samples for pans and then get started. So that's kind of a quick intro. Next time, sample pan preparation, put it in the DSC, look at some curves, and voila, that's your second lab done. All right, I'll see you in the next video. Hi everyone, we are back, and so now we are going to get prepped for our DSC lab. So we kind of introduced it last time. We'll look more at the apparatus, but now is the fun and never-ending time of sample prep. So sample prep, what do we do before anything else? Even though I know you always take these precautions in mind. Let's clean everything. So we just melted our samples, but let's clean kind of the apparatus we're going to use. So we're going to use our spatula right here. I've got my handy ethyl alcohol, so I'm just going to clean everything. So clean my spatula. You're going to see here I have this little weighing tray. We're going to use that in just a second. But I'm going to clean that just for good measure as well. Don't really need to do that, but this guy would, just for good, good housekeeping. This is basically an apparatus we're going to use, actually a tool, that's going to seal our aluminum pans. So again, we put our sample, our phase change material, the combination of lauric and stearic acid, into an aluminum pan or aluminum crucible. Why do we put it in aluminum? Well, when you melt a material from solid to liquid phase, as you all know from phase diagrams, we don't want that liquid to spill. So we need to contain that liquid, and we are going to measure, actually you can see kind of, this is a little bit dirty in here. Let's clean that guy out very well. when it changes from solid to liquid, we don't want it to spill out in our apparatus. Actually, that's one of the worst things that could happen in a DSC. So we need to seal our pans with the material inside. And then that's also going to allow us to kind of measure those thermal properties that we talked about last time in the introduction. So melting temperature, enthalpy of fusion, et cetera, et cetera, et cetera. So let's go ahead and get going with the sample. So these are the kind of aluminum pans that I was talking about previously. So we're going to use these to create kind of our samples. So the first thing that you have to do is create a reference pan. And I'm actually going to go and grab some tweezers, and I'll be back in just a second. And I'm back with tweezers. So I want to grab, basically, very carefully, using this kind of orientation, I want to grab a pan like this, like so. And I'm going to put it down right here. I'm also going to grab another pan, like so, right here. There it is. So I've got my two pans. First thing I want to do is measure the weight of these two pans. So I'm going to kind of move everything. Actually, I'm going to wipe down these guys just for good measure. So let's go ahead and take our camera, and we're going to go over to a balance and a scale. So hopefully you've used a scale like this before. This is a really, really nice scale. I actually like it a lot. So here we go. I'm going to go ahead. First, I want to zero out my tray. So I'm going to tear it. Don't want to include that. Thinking, thinking, thinking. Don't you miss this exciting, this is small change. Oh, here we go. And I'm closing here just to get even more accurate measurements. So I want to make sure that there's no kind of airflow going on. So I'm just going to put it right here. Put my other pan right here. And you can actually see these pans weigh approximately, looking at here, each 43 milligrams. So 0.0435. So for both of those pans. We're going to kind of remember that number. Look, it still fluctuates a little bit. So let's think about that number, and we'll kind of come back to that a little bit later. So 0.0433. So let's remember that. So I weighed that. Ideally, you'd kind of write that down in your lab notebook if we were in person taking notes. But now it's recorded forever on YouTube. So if I make a mistake, I'm in big trouble. Just joking. So I am going to now place my pan like this. And I'm going to, in the same orientation, I'm not going to kind of close the pan. I'm just going to put a lid on top of a lid. So you can see I still have the lip up right here. So I'm just going to place it right on top. And you can kind of see lid on top of lid right here. Like that. And I'm going to put it and drop it right at the center of this kind of little tool here. So I'm going to put it, drop it. And this is going to be my reference pan. This pan is empty. I didn't put any material in there, I promise. Just air. And I'm going to squeeze on this guy. Squeeze, squeeze, squeeze. Use all my, again, my MIT football power, as little as that is. And I'm just going to kind of pop it out. And this is going to be my reference pan right here. So this is the reference pan I'm going to use. Why do we need a reference pan? Well, we're measuring differential scanning calorimetry. It's a differential heat flow. So if I want to measure the heat flow of my material that's contained in an aluminum pan, I need to kind of zero out and measure the contributions from that aluminum. So I need to kind of consider that and just basically remove that. So we're going to treat this as a baseline. You'll notice I have these handy little baggies. So in that baggie, I'm going to write this as my reference, just so I'm not mistaken. Because you'll notice here that you don't really see any like dimple. You see a little dimple, but not really. So that's another way you could tell a reference pan, but use a baggie just in case. So I'm going to go ahead and also start to prep my sample. So one of the things I want to show, I'm going to do the same procedure. So I'm going to grab two more of these guys. And I'm going to place them back on my little, you'll see it in a second, back in my, back on my balance. All right, let's move with me now to here. Now look at this. The last one was like 0.4335, Now we're at 0.0428. So when you're thinking about possible errors in this lab, there's some mass difference. So that could cause some discrepancy. Now, how much is it really going to affect your data? Not too much. Luckily, DSC, I love DSC because it is a very robust technique. A robust technique means it's very reproducible. So we are going to want to tear that because we want to measure and write down actually the mass of our sample as well. So I'm going to tear this, zero it out, because we want to now fill our sample with about 2 to 4, with about 2 to 4 milligrams of material. So let's go ahead. I'm going to close this up. I'm going to clean off my area here, and I'm going to grab. Actually, I'm going to go ahead and grab my. I'm going to grab one of the pans. That's going to be the top, and I'm just going to fill it with material. So this was last time our 75-25. That's the material I'm going to use. So I'm just going to. We melted it. Now I'm going to mix it up with my handy wood stick to make sure we're uniform. And I'm going to grab just a little bit. Again, 2 to 4 milligrams would be ideal to make sure we don't overflow. Again, I know the lab handout says it's different, but that's why we actually do the lab. So let's go ahead. This might be enough. So it's probably a little bit too much. Let's see if I can get a good focus. Focus. Students and camera. So you get the picture. So this is where Geetha Barrera's technique comes into play. I'm going to transfer to my left hand, my offhand. I'm going to use this, and I'm going to push it off into the sample. So this is where having big, clumsy football hands is at a big disadvantage in doing experiments. But I'm fairly good. So we could put that down right now. I want to kind of remove this sample. Make sure that there's nothing kind of touching on the sides. So you can kind of see that guy here. It's probably a little bit too much, but let's go ahead and see. It's always easier to add. So I'm going to put this on the back in our apparatus. And then as I feared, look at that, 6 milligrams. Uh-oh. So what I'm going to do is just going to try to take off just a little bit of it. It's the beauty of live videos. We never know what's going to happen. So actually, I'm going to take this guy, I'm just going to kind of scrape off a little bit. And again, luckily this is polymers, lauric acid, so they're not too harmful. So I want to also make it a little bit even distribution-wise, but this is okay. So I'm going to put it back here. Let's see how we're doing. Still a little bit, but I mean, 4 is okay. 3.8, that's not too bad. We can work with that. So let's go ahead. I'm going to write that down, 3.7 milligrams. So let me get this guy set up right here. And we're going to go ahead and we are going to get a little bigger baggie right here. So I'm going to cap this guy. I'm going to bring now the sample here and here. This is my lid. This is this. I'm going to crush the lid right here. I'm going to put it, oops, sorry if you didn't see that. Put this right here. That. And it's power time. So squeeze, squeeze. Some of, you'll see some basically crucible crushers that actually have like a little like lever. Those are nice, but it's okay. We could use. It's good to get some physical exercise too, as well as your mind. Now you see here, you see that little dimple right at the center? That's when you know it's sealed. So we've sealed this properly. It's not going to leak out. If you don't see that dimple, push harder. So I'm going to go ahead and put this guy right back in our microbalance. Let's go ahead and get one last measurement of the mass. 3.6. So I'm going to label my baggie, my gigantic bag. I actually just changed to 3.5. So this was 75 lauric, 25 stearic, and 3.5 milligrams. This will be important once we run the sample. So let's go ahead and go run our sample now. We're off. And we are back. So now it's time to put our samples in the DSC. So this is kind of our program, this data acquisition program. You can kind of see the live temperature in the DSC. You always want to make sure that before you grab a sample, make sure that you're not at basically a temperature that's not appropriate. So right now we're at 24. If this says 100, don't put your hand on the machine. Again, speaking from experience. So I've got my big baggie that has my sample. Where are you at? Right here. My beautiful 75, 25 stearic. I have my reference sample right here. It's in there somewhere, right there. And then now we're gonna look at the DSC. So I'm gonna open this guy up. So this is just kind of a cooling vent. Put that over here. I'm going to pull this up. This is a very expensive piece of equipment, so we want to make sure to be very, very careful and cautious with this. This, in particular, is an extremely expensive piece of equipment. So I'm going to grab this, and I'm always going to try to keep my hand underneath it. So actually, I'm going to do this. I'm going to grab, put those tweezers in here, and I grab that sample. And I'm just going to put this guy right here for the mold. So you can see here, someone has made an egregious error. No, I've been running experiments all day today. So you can see here, on the back, that is the undimpled material, right here. The back, that's our reference sample. This is our sample. So reference pan, sample pan. So when you're putting these materials in, you want to be exactly at the center, so you don't want to kind of touch. You can see the thermocouples right there. So what happens is here is we're going to ramp up the temperature, and then it's going to take this pan, and it's going to put them at the same temperature, and it's going to say what's the heat required to get those pans at a different temperature. And that difference in heat flow, that delta H, that's what we measure in our experiment here. And we're going to be able to deduce a lot of cool properties from that. So, all right, so I'm going to go ahead and grab these and get them out of here. Be very, very careful not to kind of touch those. So go ahead and grab this guy too. Sorry, it's hard to do. Excuse me. So, go. And you can see, actually, unfortunately, a little bit of the mess right here. So we're going to try to clean that out. But it's going to be all right. So let's go ahead and put our sample in. Again, you don't want the material to kind of leak out. So we're going to go ahead and grab our sample. So just stay with me real quick. Those are the old ones. So we're going to put our reference pan in. So here. This is our reference. Oops, excuse me. This is our reference pan. So I'm going to put it right there. Drop it in, put it right there. There's our reference pan. Here, and then let's get our sample right here. That's me. Grab this guy. So let's go ahead and grab our sample pan right here. Sample pan, and let's put it. Drop it in the bucket. So let's go ahead. Just like that. There you go. Sample, reference pan, sample pan, and let's go ahead and put everything back together. So I'm going to put here. So on top. Put this guy on top of that guy. And so the thermocouple. Let's put this lid on top too. Excellent. So now it's time to set up our experiment. So what I'm going to do is go ahead and do File, New Experiment. I am going to do a experimental procedure, my name. I'm going to say, 75L, 25S, spring 21. Whoops, you didn't see that. The mass of our sample is going to be 3.5 milligrams. You'll see that becomes important in a second. Let's go ahead and delete that. Molar mass, we don't need at this point. Let's go to procedure summary. Let's go down here. Let's go to procedure properties. But actually what we're going to do is add this up here. So this is add a standard zone. So we are going to go and ramp up from an initial temperature here, 20, yeah, we can say 20, and let's go to all the way up to 100, and we are going to go at a ramp rate of 10C or 10K per minute. So that's our speed, our ramping speed. So you'll see some data sets that I give you where it's not just a ramp up, but basically melting and cooling curves. So depending on the speed, you could get this concept of basically supercooling or degree of supercooling. So we'll talk about that when we get a little bit closer to our analysis section. But this is how we're going to run the experiment. So those are my procedures, my protocols. I've labeled the sample. So now all I have to do is press play. Play here. And here we go. I heard it ramping up. Look at it. I love this machine. The S has written so this is fantastic. Now, you want to be very sure, obviously, you could be running this, you can see the temperatures here. Range of minus 170 to 700. Be careful. I've experienced a lot of people getting burned from this DSC. That's not a kind of turn of phrase, literal burn. So we want to make sure that we stay away from that. So let's go ahead and we're going to watch this live for a little bit. And I am going to actually, if you don't mind, I'm going to pull up a chair because my knees hurt. I'm old. So let's go ahead and see what's happening. So right now, nothing really cool. You could see the blue is basically it's a measure of the heat flow in microvolts. But we're going to see soon, we'll actually start to see something. The red is the temperature of the furnace. And the black is going to be actually the red is our sample temperature. So it's the temperature of our sample, excuse me. And versus time, so you can tell the furnace temperature as well. So something's starting to happen here, but it's still pretty small values, small changes. So we can see that the temperature there, 23, 24, it's increasing because again, we're ramping up at 10 degrees K per minute. So let's see what happens with this curve. So we're waiting. It's okay. This is real life experiments, people. Isn't academia. Who wants to be a PhD? Can you do 5 to 10 years of this? If not, it might not be for you. If you really like this, then you're the best career you could ever ask for. Do a PhD, then do a postdoc. Do 5 more years of a postdoc. So, but, okay, we're still seeing, increase in the temperature gradually. Nothing really exciting is happening yet. Did I mess up my experiment again? Who knows? We will see actually in a bit. So again, the temperature is increasing because there's some heat flow because the material is absorbing some. As we know, we have thermochemical, sensible, and phase change kind of heat storage concepts, right? So right now we're in sensible, so we're still absorbing some heat. We'll talk about it in our lab analysis, and actually a little bit after this. But we're going to have to kind of convert these units of heat flow to our usual units of milliwatts, and that involves using a calibration tool, which is indium. So basically you put indium in this material, and then you see, okay, indium is a well-characterized material, so you can convert microvolts to milliwatts and everything else in between. Uh-oh, okay, something strange starting to happen. You see that change in that slope? It's not a second order phase transition like TG. Look at it. You see it? We're starting to really look at heat is it being absorbed or is it being released? Melting absorbs heat. It's endothermic. So we are absorbing heat here. Look at, we're melting. We're melting, people. So we are melting our material right now. You're going to see it's basically there's going to be a peak that occurs. So if you see a single peak that's melting, is that single, first order phase transition. Now in some of the curves that you're going to produce, you're going to see essentially multiple peaks. and little humps, and we'll look at that in the data analysis, but that can indicate a liquidus temperature, a solidus temperature, or another type of transition like we talked about in class. It could be a solid-solid, it could be FCC to BCC, it could be a eutectic transition, it could be, who knows. How would we figure that out? Well, taking a break from here, we would put the sample in the XRD, and we'd run temperature, and we'd look at how the structure changes. Luckily, I'm so nice that I'm not going to make you do that, but I will give you the literature that kind of shows you what can be done. An experiment that actually utilizes this same experiment to develop a full phase diagram. I want to look at the full time window here, so I'm going to just go ahead and I want to do total experiment. So you can see now, right? That is a huge single peak. So we'll go back to the data analysis. I'm going to let the rest of this run, and then we're going to get into how you analyze this data. All right, I'll see you in a bit. And we are back, and we have finished our analysis, and you can see everything's pretty much like we kind of ended up with. So no additional peaks, really a single peak. This little hump here is a little bit of like a noise, so I wouldn't classify that as a peak. So I'm going to now go into my processing folder. So I'm going to open up the file that we just did. I'm going to, this right here. So let's go ahead and analyze this data. So exo up, so endo down. So we are endothermic, we are absorbing heat. Excellent, that makes sense qualitatively with what we saw. So now I'm going to do this one operation that we need to kind of do here. So we need to do a math operation, and we need to do, actually first I need to click on the curve. I need to do a math I need to do a math operation, and specifically baseline and integration. So I need to integrate this peak. So I'm going to pick over here, pick where this becomes flat, and I'm going to integrate this value. So this does all my integration. I'm not super mean where I mean, you could do this Mathematica too, but it's kind of hard to do the calculations because it automatically gives you these units of heat. So this is our delta H. It's the the heat released or heat absorbed upon melting. So our delta H endothermic, or delta H of melting. So this is 681.382 microvolt seconds per milligram. Not nice units. We want joules per joules per gram. You'll kind of see that in the analysis. So we are going to take a picture of this, and we're going to kind of go back and analyze it in our kind of result sections. But that's it. This is all you're going to have to do. Now you can do a lot of other cool things with this DSC analysis. So you can measure TG. There's a couple of videos that I'll post on my Mech 202 class. So there's lots of kind of cool things that you can do with this type of analysis. You're going to look at some curves where we cycle. So we heat and cool, and you can see how well the thermal, what's the kind of reproducibility of our curves, what's the thermal stability of these phase change materials. We want to look at if there's any degree of supercooling. We want to look at how much heat is released. We want to look at melting temperatures, and we want to think about all these thermal properties and which would be the best for the application that we are most interested in. So you see, that's why we kind of plug in that mass initially, because it's used to kind of calculate these values. So when you integrate, you have to kind of consider the mass as well. So excellent. This is it. We're going to go into some data analysis now, and we're going to create some amazing posters, and we're going to have a really fun kind of Zoom poster session. So I will see you all in the next lab, mechanics. So you're going to be able to break things coming up. I know. No more obtuse labs and some cool thermodynamics. Instead, we're going to use this machine, and we're going to break things. So I'll see you all in the next lab. Thanks. Bye.